Once again, this is a very simple inductive circuit, RL circuit in DC case, and when the switch is closed there will be transient current, but I will try to have a different approach for this one to solve the current equation, which is I, the series current, for both transient and steady state. As so I transient, the full current will be I transient plus I steady state, and of course transient current is the current, the initial one that happens because of the time constant, L over R, and steady state is when the transient is gone. So steady state is the DC condition when the inductance in this case will be short circuited and the current. So what we know, or what we actually, it's for all practical case, the transient current is essentially an exponential decay pattern of exponential decay form. It's always like that. So I transient will always have the form of A, which is a constant, unknown one, E minus T over, I can write tau as the time constant. So this is the practically standard form for any transient current, any transient component of the current, or transient current rather. And tau in this case for LR circuit, it would be L over R, and if it were an RC circuit, it would be RC. So let's not do the RC one here, we will just do the LR one. So this one is the transient form, and we can see that the I steady state, which is also can be called I infinity, or when t is equal to infinity, the current becomes, the inductance will be short circuited. So I steady state is E over R, as simple as that. So the total current will be A e to the power minus t over tau plus E over R. So this one we know. Now we will have to use boundary condition when t is equal to 0. Let's see what it takes. So let's say when t is equal to 0, I is, that means when the circuit was just closed, I is, say I naught. So this one is I naught. This whole term at t is equal to 0 becomes 1. So A plus E over R. So this way A we can get I naught minus E over R. That makes sense. So we have just found the value of A, which is I naught minus E over R. Now if we rewrite this equation, A, instead of A we can write, I naught minus E over R and e to the power minus t over tau plus E over R again. So this current form is becoming like this. I is becoming I, this is 0 because I naught is at I, t is equal to 0. So when t is equal to 0 we can say I is 0. When t is equal to infinity, which is the steady state, we can write here we can write I infinity. So I naught minus I infinity, which is the steady state one, and then this one I will use a different bracket there, this one tau, and then plus I infinity. So this is the form, standard form for the current for inductive case, RL circuit. So I initial current minus I steady state, and this one will decay with e to the power t minus t over tau, and then finally the steady state current. So over time only this one will exist. So when t is infinity, I will become just I infinity, of course, which is of course I steady state. Now for one case we can assume that, just for one particular case, let's say the inductive current was 0 at t is equal to 0. So at t is equal to 0, I0 is 0. In that case, this equation will become this one will be 0, the first part. So this is I infinity e to the power minus t over tau. Tau is always L over R, so it's becoming t into R over L, and then plus I infinity. And then if we rewrite it, it becomes I infinity and then 1 minus e to the power minus t over tau. And this one is the equation where exponentially rising. So over time this one becomes 0, and initially this one is because initially at t is equal to 0, this part is 1. Sorry, this part, I'm just trying to use another color. This part is 1. So at t is equal to 0, the whole term is 0, and when t is equal to infinity, this part becomes 0 because t is, so this is e to the power, and when t is equal to infinity, the denominator is very large, so 1 over infinity is 0, so this part becomes 0 at t is equal to infinity, and at t is equal to 0 this part is 1, the same thing. And so this one stays, so initially this is 0 and this is, so it will be an exponentially rising situation, but it will be this of this form when at t is equal to 0 the inductive current is 0. So yeah, it's just I just tried to look at this one in a different form, the same RL circuit, but instead of going into solving the differential equation, so I mean this is of course the result of differential equation, but instead of writing the KVL in terms of the differential, so L di dt plus Ri whatever, and then looking at the natural response and forced response, we can just write this form directly, because transient response itself, just the transient part will always be exponentially decaying, and then there will be a steady state part, and depending on the circuit the steady state part will vary. It can be a steady state value, it can be 0 as well, so it will all depend on the particular situation. So maybe I will do this one for another switch condition, so I don't want to make this video too long.